And we're live. All right, guys. So we're continuing our little journey into chapter 4, where we're learning about Newton's laws. And what's going to happen is, again, every Newton's law problem is the same. All that ever changes is some of the tricks that you might utilize to talk about them. And here is the trick that we're going to talk about today. I want to talk about forces of contact. And this is where we're going to get Newton's third law a little bit of a workout. And it's probably easiest to approach this with a specific example. So let's go ahead and try a specific example. So let's imagine that I have the following. I've got two boxes. Here's a little box. I'm going to call you box 1. And it's butting up adjacent to a larger box, which I will designate as box 2 because I'm incredibly creative. All right, and they're both sitting on the ground. And what's going to happen is the mass of box 1, let's have that be something like 5 kilograms. But box 2 is obviously bigger. So let's have the mass of box 2 be considerably larger. Now, here's what's going to happen. I'm going to walk up and I'm going to push box 1 to the right. With 100 newtons of force. Now, what I would like to figure out is the acceleration of the boxes. And as a bonus, I'd like to figure out the force that's exerted between box 1 and box 2. So that's the thing I want to figure out. So what we're going to do is we're going to do this like any other Newton's law problem. And remember, every Newton's law problem has 4 basic steps, right? Step 1, we're going to draw a free body diagram, figure out what forces we have in play in this problem. Now, I've got 2 objects here. So what I'm going to do is I'm going to do a free body diagram for each object. And with them kind of in the picture here a little close together, it might be confusing as to which forces are acting on which boxes. So when I do my free body diagram, I usually kind of draw them in isolation. So it's easy for me to figure out which forces are where. So here's box 1, and I'm just going to label out his forces. And over here, box 2, I'll draw separately, and I'll draw a free body diagram from it as well. So let's start with box 1. What forces are going to get exerted on box 1? Well, one force obviously is me. I'm pushing box 1 to the right with 100 newtons of force. So let's have that 100 Newton force. It's to the right. I'm going to call it P for push, right? And I know that P is 100 newtons. So that's the one force the problem told me about, but it's not the only force that box 1 is going to experience. Now, gravity obviously acts on box 1. Gravity pulls downward. We know that the force of gravity is whatever your mass is times g. So I've got that force pulling it downward. It's on the ground, and it's feeling a force from the ground. And we learned last time that we typically call that the normal force because it's perpendicular to the ground. That's the word normal just means perpendicular. We don't know how big that force is, so we'll just leave it there, call it as n. Now, for ease of calculation, let's assume that the ground is frictionless. So I don't have to worry about any kind of friction as this thing tries to slide across the ground. We'll deal with friction in the next chapter. So right now, we're doing lots of frictionless surfaces just because we don't know how to do otherwise. But the other thing that's touching box one is touching box two, which means there should be a force that box one feels because of box two. Now, it's like a normal force, right? The force it feels is going to be perpendicular to the surface of box two, and where they're touching, that's going to be to the left, which, when you think about it, that makes sense, right? Box one, if box two wasn't in the way and I pushed it, it would move to the right a whole lot faster. But what's happening is, because box two is in the way, it's going to push box one to the left and cause it to move slower than it would have otherwise moved. So I got to give this a name. Sometimes we'll call this F12. Let's just go to crazy. Let's call it B for box. Doesn't matter. The names of the forces are not important. You can name them whatever the heck you want. So I want to call this force B. It's because it's the force from the box. That's it. So P for push, B for box, I'm good to go. Now, nothing else is touching box one, so that's it. Those are my only two forces that I have acting on box one. Now, what about box number two? Well, box two, it feels gravity, so gravity is going to pull it downward. Now, I should probably draw a distinction because the M over here is mass 1, so I'm going to call that M1. The mass over here is mass 2, which is a different number, so M2. By the same reasoning, the floor is going to push box 2 up with some kind of normal force, but this normal force and that normal force, they don't necessarily have to be the same size. So let's call them N1 and N2 just in case they're different, because they will be. Now, what else is touching box 2? You might think, oh, the 100 Newton push, but that's not the case, because I'm pushing box 1. I'm touching box 1. I'm not touching box 2, which means I'm not exerting any force on box 2. In order for me to exert a force on box 2, I would have to touch it, and I'm not. However, box 1 is touching box 2. So box 2 is going to get pushed to the right from box 1. How much force will that be? Well, according to Newton's third law, whatever force box 2 pushes box 1 to the left, box 1 will push box 2 to the right with the exact same force. So it's going to feel a force to the right. It's going to be the same magnitude as this force. So I'm just going to call them both B. They're the same letter, and I don't have to call it B1 and B2 because they, according to the third law, they must be the same. So in terms of the free body diagram for box number 2, that's it. That's all we've got. So step 1 of every Newton's law problem is to do those free body diagrams and identify your forces. We have done that. We've done that for each of the 2 boxes. So step 2 for every Newton's law problem is to choose your coordinate system and to break your forces down into that coordinate system. So let's just go with a regular boring coordinate system. Let's have to the right be the positive x direction, and let's have straight up be the positive y direction. So what's going to happen here is you'll notice all of my forces are either purely horizontal or purely vertical. I don't have any annoying diagonals in this question, and that's going to make my life way easier, right? When I go to take inventory, they're either all going to be in the I hat direction or they'll be in the j hat direction, but there won't be any of the forces that are split between the two. And that's going to make it easier for me to do the calculation. So real quick, let's do box number 1, right? So if I do box number 1, I'm going to have N1 is purely up, but not sideways. So it's 0 I hat, but whatever N1 is, that'll be in the j hat direction. For the weight on box 1, I'll call it W1. It's 0 I hat, but because it's downward, I'm going to slap a minus sign on it. So negative m1g in the j hat direction. For the push, well, it's to the right, so it'll be p I hat 0 j hat. For the force from the box, call that b, it'll be negative whatever b is I hat, but 0 j hat. So this is all for box 1, which I'm writing that down just because it's important, because I had to do for box 2 and I was stupid and I had free space. I should have done box 1 over here and box 2 over there. It's confusing. All right, so for box 2, I'll do the same thing. Right, I've only got 3 forces on box 2, but same deal for it. N2 is going to be 0 I hat plus whatever N2 is j hat. For the weight, it'll be 0 I hat minus M2 j hat. And for it, the force from the box is exactly the same, except it's to the right. So it'll be positive b I hat plus 0 j hat. So normally I would just skip this entirely because it's pretty obvious, but just in case you were still trying to wrap our head around this component form thing, since all these things are either horizontal or vertical, they're always either in one direction or the other, but never both. If they were diagonal, these two terms would both be non-zero. Whew. So we've gone through and we've taken inventory of all of the forces on both of my objects, the same way we would for any other Newton's law problem. Now what's going to happen is step 3 is I'm going to start generating some equations. And I'm going to generate those equations by using Newton's second law. Newton's second law says the sum of the forces equals ma. F equals ma. I'm going to do it for each box. And because the sum of the forces is a vector sum, I'm going to have to do it once for each component. Because when you add vectors, you add x's to x's and y's to y's. So what I'm going to end up with is a total of 4 equations. I'm going to get 2 equations for box 1, one in the x direction, and then another one in the y direction. And I'm going to get 2 equations for box 2. Again, one in the x direction, one in the y direction. Total of 4. So let's break those down. Let's keep that in view so you can kind of see what we're doing. Hopefully this won't be a mystery. Let's do box 1 first. And let's do the sum of the forces in the x direction for box 1. So in the x direction, I've got 0, 0, p, and negative b. So for box 1, I'm going to have p minus b. That's the sum of the forces in the x direction. And that's going to equal the mass of, well, since we're doing this for box 1, it'll be the mass of box 1 times the acceleration of box 1 in the x direction. What about the y direction? That won't be quite as interesting. In the y direction, I have 2 forces, this and this, because those two are 0. So it'll be n1 minus m1g. That's going to equal the mass of box 1 times the acceleration of box 1 in the y direction. So those are my 2 equations for the first box. What about the second box? Well, for the second box, in the x direction, heck, I've only got 1 equation, or 1 force, because I have 2 zeros in this. So the sum of the forces in the x direction is just b. And of course, that's going to equal the mass, but now we're doing it for box 2, so the mass we'll use is mass 2 times the acceleration of box 2 in the x direction. So those are subscripts. In the y direction, I have 2 forces, n2 minus m2g. That's going to equal the mass of box 2 times the acceleration of box 2 in the y direction. So those are my 4 equations. Now, usually when I get to this point in any problem, I always pause for a moment after I've written my equations. And I pause to ask myself if I know anything at all about the accelerations of the objects in this problem. And it turns out that for this problem, I know quite a lot about the acceleration. One thing I know is that if I walk up and I push this box to the right, the stuff's going to move to the right. Pushing this guy to the right is not going to cause it to fly up into the air. It's not going to cause it to sink up into the ground. If it moves at all, it's going to move sideways. So what that tells me is that for box one, it might have an acceleration in the x direction. This could be non-zero, but there's no way it's moving up and down. The acceleration in the y direction has to equal zero. So, if this is zero, this whole thing zeroes out. I can make that be zero. Now, the same is going to be true for box two. Box two, if it moves at all, is going to move sideways, not up and down, right? They're going to move along the floor. So A2y, also zero. That makes that super easy. Now, what about the accelerations of the two boxes sideways? Well, in the sideways direction, imagine this is box one or this is box one. Ah, crap. This is box one, and this is box two, right? So what's happening is if I walk up and I push box one and they move, they're moving together, right? This guy's not going to accelerate more than this guy. They're going to move in tandem as I push them. And so what that tells me is that even though I was super careful when I wrote my equations, because I wasn't sure at that moment whether the acceleration of box one in the x direction was going to be the same as the acceleration of box two in the x direction, from common sense, I know they've got to be the same. So even though I called them A1 and A2, they're going to be the same. So I can drop the subscripts. And what's more, since there's no acceleration in the y direction, the total acceleration is going to be the acceleration in the x direction. I can even drop these subscripts. I can just call them A. I always like to be a little bit careful when I first set it up, just in case, but once I get here and I kind of pause and think it through, I feel confident that they're going to have the same acceleration and it's going to both be in the x direction. So I'm just going to call it A and make my life easier. And what's cool is that this A and this A have to be the same so that when I go to solve these equations, I'll be solving for the same variable in each equation. Neat. So now I've got four equations. And what is it that I'm looking to find? Well, I asked to find the acceleration of the boxes. So I'm solving for A. And I also asked to find the force that box one exerts on box two. Well, that's B. So the two things that I'm looking for are A and B. Notice in these equations, P is given, B is not so much, A is not so much. So there's two variables in that equation, can't solve it yet. Down here, two variables in that equation, can't solve it yet. The masses, at least, I know. Over here, I don't know what N1 is, nobody told me. If I wanted to solve for it, I totally could, because N1 minus M1G equals 0. I could go ahead and solve that and find that N1 would equal M1G. By the same reasoning, I could solve this equation. N2 equals M2G. Nobody asked that, but it tells me that for this problem, the ground is going to push the box up just as hard as gravity pulls the box down. That's why it's not rising or falling. So helpful, but not for this problem. So these two equations aren't even useful at all. These two equations are where all the action is. So I want to go ahead and solve these problems. I have two equations and two unknowns. The trick for solving two equations and two unknowns is substitution. So you'll notice that the force between the two boxes appears in both places, but if B is equal to M2 times the acceleration, I can take this expression here and plug it into the other equation, replacing B. So now I have P minus M2A, well, I was going to say A2, but I don't need to, M2A equals M1A. And the only thing I don't know in that equation is the acceleration. Let's get the acceleration by itself. I got to combine like terms. So I'm going to add M2A to both sides. So I'm going to have P equals M1 plus M2A. Right. This is, remember, M1 was 5, M2 was 10. So it's like saying 10 plus 5, 15A, right? That's what that is. So now if I go to find the acceleration, I'm going to divide P divided by the total mass. And that's going to tell me the acceleration, which in this case is 100 divided by M1 plus M2. That's 5 plus 10, so 15. So what's 100 divided by 15? 6 2/3. So I now know the acceleration of the two boxes. They're going to accelerate at 6.67 meters per second in the positive direction, so to the right. Yay.
I have a question.
And, yes, ma'am.
Where did you get the numbers for M1 and M2?
Back on the first page.
Okay. Oh, I forgot. Sorry. Okay.
Yep. Yeah, so that's where the numbers came from. They were in the problem originally. I like to hold off plugging in numbers for as long as possible. You're going to see why here in a minute, because we're going to save ourselves a whole ton of work for the follow-up to this question because we did it this way and didn't plug the numbers in way up here, right? So that's the acceleration. Now, I also want to find the force between the boxes, which was B. Now, conveniently, B is equal to M2A. Well, M2 was 10, right? So B is going to equal 10 times 6.67. That's easy enough. So the boxes are going to push against each other with a force of 66.7 newtons. Neat. So that was an easy enough problem. Now, here's a question. What would happen if I were to take the same scenario, but I'm going to swap the order of the two boxes? So instead of me pushing box 1 into box 2, now I'm going to switch them around and have box 2 on this side, box 1 on this side. I'm still going to push them to the right, but this time I'm going to push box 2 into box 1. And I'm going to solve the exact same problem. And the question is, would I get the same answer or not? Would the answer be different if I swapped the order of the two boxes and I pushed the heavy box into the light box? What would change? Would anything change? Would I get the exact same answer? All right, I'm going to try something because most of you guys are sitting there not responding.
Can you repeat the question?
Yep. All right, so let's try this. I've never done this before, so I'm not sure how this works. I'm launching a poll. So for those of you who are viewing live, Would the answer to the question be the same if I swapped the order of the two boxes? If I pushed box 2 into box 1, would I get the same acceleration and the same force, or would it be different? So far, I've got one person who's chimed in. 2 people have chimed in. All right, we have a split now. 2/3 of you have voted one way, 1/3 of you has voted the other way. Apparently, 2 of you are just checked out, not paying attention. Makes me sad. All right. So, the result of this poll were that 2/3 of you said that no, I would not get the same answer, and 1/3 of you said I did. Now, what would be different in this problem? Let's go back. And let's figure this out. If I go back to my camera someday. Uh-oh. There we go. Zoom started to act a little wacky for me. There we go. So if I swap this around, what's going to happen is originally box 1 had 4 forces on it. Me pushing, the other box pushing it, the normal force and gravity. And box 2 only had 3 forces on it. When I swap the order of the 2 boxes, what's going to happen is the free body diagram for box 2 is going to look exactly the same as the free body diagram used to look for box 1. In fact, all I'd really have to do to solve the problem again is just swap the numbers. I'm going to call U box 2 and that mass 2. I'd call U box 1 and that mass 1. Of course, that's going to swap all these numbers. But then if I swap all those numbers, I'll be swapping these numbers here. Over here, nothing important is going to happen, right? I'd swap these 2s and these 2s and these 1s with these 1s, but I'd still end up with N1 equals M1G, so this would be the same, and that'd be the same. So this right here is the same, nothing new there. But here's something that is different, because look what's going to happen. Up here, I got to swap this 2 and this 1. So this would be mass 2, that'd be mass 1. When I go to combine my things, I'd have P minus M1 equals M2 times A. But when I move that over, I'm still going to have M1 plus M2. The order that I add them in is irrelevant. So the accelerations would be exactly the same as they used to be. They're going to have the same acceleration regardless of which one of those things I'm pulling on and which one I'm not. However, notice now B is M1 times A, and M1 was 5, not 10. So when I go over here, it won't be this anymore. This is different. And instead, what's going to happen is B would equal 5 times 6.67. Which is half as much as it used to be. What the heck? When I swap the order, the force between the 2 objects is different. The accelerations were the same, but the amount of force required was different. And one way to think about it is when I push box 1, it's got a mass of 5, right? In order to make a box with a mass of 5 accelerate at 6.67 meters per second squared, you're going to need a net force of a certain size, right? So what happens is I got 100 newtons pointing this way, but if I had just 100 newtons and no force pushing backwards, it would accelerate way, way more than that. If this guy wasn't here at all and I pushed with 100 newtons of force, the acceleration would be 100 divided by 5, 20. That's way, way faster. So by this guy pushing backwards with a force of 66 newtons, the net force is going to be 100 minus 66.7 is 33.3, and 33.3 divided by 5 is 6.67. Neat. Meanwhile, this guy over here, in order to make this guy accelerate at this acceleration, I have to have a force of 10 times 6.67 or 66.7 newtons. So what's going to happen is the net force works out just right to make the accelerations be the same. However, when I swap the order, now what's going to happen is in order to make this guy accelerate to the right with this much acceleration, I have a 100 Newton force pushing this way. I can only have a 33 Newton force pointing that way so that the net force is 66 Newtons. So the net force experienced by just box 2 is still 66. Why? Because of the 33 pushing back this way. So you can kind of think of it as I'm pushing this guy with 100 Newtons of force. It's using some of that 100 Newtons, in this case 33 Newtons, to make it accelerate. The other 66 is left over to make this accelerate. When I push this guy first, he's going to use 66 of those 100 Newtons to make himself accelerate. I've got 33 left over to make him accelerate. Now, why should you guys care about this? Well, turns out that a lot of you guys are mostly biology majors, and a lot of you guys have an intention of going to medical school someday. So here's how this weird bit of physics, me pushing 2 boxes around, might make a difference if you're in a medical field. So true story. I have a cousin named Kyle. Kyle is not very smart. He's always been a little bit slow. And when Kyle was very, very young, maybe 2, his mother accidentally dislocated his shoulder. Now, here's how it went down. I think his mom was standing kind of on the sidewalk. She was talking to a friend of hers from like next door or something. And Kyle was running around the front yard like an idiot, because that's what he does. He's running around like crazy. And I guess what happened was Kyle started to run out in the street, and there was traffic coming. And his mom saw Kyle run into the street and freaked out, thinking he was going to go run and get himself run over. And so she reached out and took his arm and grabbed and pulled him back onto the sidewalk where he was safe. Now, here's the problem, right? Kyle had a certain amount of mass. We think of Kyle as one object, but in reality, you can think of your body as being a composite of several objects, right? You know, you've got an arm that's connected to the rest of your body. And what's going to happen is when she grabbed him by the arm, she pulled his arm with a certain amount of force. Now, his arm has one mass, and when it moves to the right, his arm is going to have to pull the rest of him with sufficient force so that his entire body moves together with a certain acceleration. Just like in this problem, box 1 had to push box 2 so that they'd move together with a certain acceleration. Now, what's going to happen is because his mass for his arm is smaller than the mass of his body, that would be like having the small object push against the big object. So it's kind of like in case 1 where box 1 was doing the pushing and making box 2 move. And when that happens, the net force, or the force exerted from the arm on his body, was larger, right? When in case 1, when box 1 was pushing box 2, the force between them was 66 newtons. It was the bigger number. Now, here's why that's a problem. The tendons in his shoulder can only exert so much force before they start to stretch. And what happened was she grabs his arm and pulls him, and the tendons in his shoulders are having to exert a force on the rest of his body to pull his body along with him. And that force was too large, and they start to stretch a little bit. You stretch those tendons too much, and all of a sudden, your shoulder pops out of joint, and you've dislocated your shoulder. Ouch! That's a nasty injury, right? Now, had my aunt taken physics class and paid attention, she would have realized that that was a bad idea. And what she could have done is, instead of grabbing Kyle by the arm, if she'd grabbed him by the waist and pulled him with the exact same amount of force, what would have happened is she would have pulled him with the same acceleration. He would have gotten out of the street every bit as fast. But now what's happening is his torso would have had to exert a force on his arm so that his arms come out of the road with the rest of him. The difference is because his body has a much larger mass, the force that his tendons would have to exert from his body to his forearm would have been smaller. And those smaller forces probably would not have caused the dislocation in his shoulder. So it mattered not just how hard she pulled, but where she pulled as to what kind of injury it incurred. And you get this kind of thing all the time. If you've ever like caught a baseball and jammed a finger, the same thing is happening, right? If you catch the baseball in your palm, then what's going to happen is the baseball exerts a force on your palm and moves your entire hand a little bit. But your hand moves, it pulls your fingers with it. The mass of the fingers are smaller, so the force your hand has to exert on your fingers is relatively small. Your knuckles are okay. If, however, you catch the ball improperly, if the ball comes in and it hits your fingertip instead, then what's going to happen is the ball is going to exert a force on your hand's going to accelerate just as much. The difference is that now your finger is having to push your entire palm, or heck, your entire forearm. And the force it's going to have to exert to move that big mass is much larger. And if that force that your knuckle has to exert is too large, that can cause injury. So many injuries end up occurring not because of the types of forces that you're exerting, but how those forces are being exerted. And by having the small object have to push the big object around, the forces between them end up being much, much larger and therefore more likely to cause injury. Pretty neat. So far, so good. You guys okay with that? So this class of problem is what I call a connected object problem. And the trick in a connected object problem is when you're doing your free body diagram, you always want to do a free body diagram separately for each of the two objects, or sometimes more than two objects. So you'll do a free body diagram for each object. You'll break the forces down for each object, and you'll get equations for each object. And you'll notice along the way when we solved this, look what happened, right? We took these two equations and we put them together, and we ended up with P equals M1 plus M2A. And that happened regardless of whether box 1 was going into box 2 or we swapped the order. This was the same both times. And one way you can kind of think about that is that, well, this is like F. This is like the forces if I treat the two boxes, if I imagine that they are instead one really big box whose mass is just equal to the sum of those, well, the only force on that big box in the sideways direction would be P. So this is like doing a free body diagram where I treat both boxes together like one giant object, right? It's F equals MA, right? And that would give you the acceleration just fine. Just like if I was talking about my cousin Kyle, if I treat his shoulder and his torso as one big Kyle-shaped object, right? The force my aunt pulled him with would equal Kyle's total mass times Kyle's total acceleration. I could treat him as one big object, and I'll get the right answer for his acceleration. But it won't tell me anything at all about the forces that keep the objects together. So if I want to know about the forces that keep these things moving together, there I'm going to care about this. If I was doing this for my cousin, then what would happen is I'd have to have some term kind of like B, where it's the force of his shoulder exerting on the rest of him, and I'd be solving for that. And that would be different. And I'll never be able to figure that out if I treat them as one giant object. That's where I've got to break it down bit by bit, like we did up here, to figure out how much those internal forces are holding that object together. So connected object problems, you'll know them when you see them because you'll have two objects that are both in motion at the same time. And it can come in a number of different scenarios. Here's the exact same problem, but with a twist. Watch this. What if I do something like this. Yesterday we did a box on a ramp. Here's a ramp. And let's say that's a 30-degree incline. Now, let's again keep no friction. This is a super slippery ramp. But I'm going to take one object, object 1. I'm going to stick it on that ramp. And let's say that the mass of object 1 is 10 kilograms. And then what I'm going to do is I'm going to take a piece of string. And I'm going to tie that piece of string, run it up here, drape that piece of string over a pulley that can rotate. And then hanging off the edge, I'm going to hang a second object. And let's have this object be, I don't know, 12 kilograms. If I set that up and then release it from rest and let it go, what's going to happen? Well, to solve that problem, I have two objects that are connected because this string connects these two objects. If this guy here falls, it means he's going to rise. If this guy here slides down, it means he's going to rise. So the accelerations of those two objects, they're going to have to be related because if they accelerate different amounts, that string would snap. So in order to solve this problem, I'll do it the exact same way. I'll do a free body diagram for each of the two objects and then solve to see what happens. So for object 1, what are the forces acting on object 1? Well, gravity is going to pull object 1 straight down to the tune of whatever m1 times g is. That's the force of gravity on object 1. Now, object 1 is touching the ramp. So because it's touching the ramp, there's going to be a force from the ramp. That's what we call a normal force. It's perpendicular to the ramp, so it's not straight up. It's kind of diagonal. It slants straight up. Now, what else is touching box 1? The string is touching box 1. Now, when we talk about strings, the term you'll often use in context of strings is something called tension. We talk about the tension in the string. Now, what is tension? Tension is the tendency of a string or rope or whatever to be pulled apart. Here's why that matters, right? If I've got a piece of string and I yank one side but the other end is free, then all that's going to happen is I'll pull the string, the whole string will move, and there will be no tension in the string. It's not being pulled apart. But if I take a string and I pull one end and the other end is pulled over there, then what's going to happen is the string is going to get tension in it. It's got a tendency to be pulled apart. And what's going to happen is when I yank here, this end of the string is going to pull my hand this way. This end of the string is going to pull my hand the other way. And the tension in the string is going to be whatever force that is. And so oftentimes we think of the tension as just the force transmitted by a string. The idea is that this end of the string is pulling the box up the ramp with some amount of force, which I'm going to call T for tension. And so long as the string has a negligible amount of mass and it doesn't take any force just to move the string by itself, and as long as this pulley has no friction and no mass, it won't cost us any force to make the pulley spin, then whatever tension we have at this end of the string is going to be the same as this end of the string, except this end of the string is going to pull the box upward because strings pull, they don't push. So that's the idea, is that if I have a massless string, the tension at either end will be the same. We call it the tension in the string because it's exerting the same force on either side. Nifty. We'll revisit this problem in chapter 10 and we'll learn how to solve it if this pulley does not have zero mass. But we're going to have to learn some more stuff before we can do that. Meanwhile, we got three forces on object 1, because there's nothing else touching object 1, so that's it. Object 2, we found one force, the tension of the string pulling it upward, but gravity is also pulling it downward. So in terms of our free body diagram, that's it. We have 2 forces on object 2 and 3 forces on object 1. So when I go to solve this problem, the next step is going to be to choose a coordinate system and to break my forces down into that coordinate system. And I'm going to have to do this for both boxes. So let's do it one at a time. So let's ignore him for a second and not worry about it. Let's do this one first. Now, for this guy here, I got to choose a coordinate system, but I'm on a slant. And the trick that we've learned for things on a slant is rather than choose X to be sideways and Y to be up and down, instead, let's take our coordinate system and slant it so that one component is parallel to the ramp and the other component is perpendicular to the ramp. So let's have my X direction run straight up the ramp. And that means that my Y direction will be straight perpendicular to the ramp. So the coordinate system I'm choosing here is a slanty coordinate system. That will make my life easier when I do F equals ma. Now, if I do that, conveniently, this force of the string, the tension, is in the same direction as X. So my tension force is going to be whatever the heck T is, I hat, but 0 J hat. That was super easy. The normal force will be similarly easy. It's going to be not in the X direction at all, but it will be in the Y direction because this is the same direction as that. The tricky part is going to be this force of gravity. We're going to break that down the same way we did yesterday. So there's the Y component, there's the X component, and this angle for my ramp is the same as this top angle right there. So when I go to break those into components, I'll use SOHCAHTOA. The hypotenuse, which is the straight down gravity component, that's M1G. The X component is the opposite side of the triangle. So the X component is going to be M1G times the sine of 30 degrees in the I hat direction. Plus, I said the X direction is up the ramp positive. Gravity is trying to make it go down the ramp. I got to slap a minus sign on that. By the same reasoning, the Y component over here is the adjacent side of the triangle. For that, I'll use the cosine. So that'll be M1G times the cosine of 30. It's into the ramp, not out of the ramp. So that will also be negative. So those are the 2 components for the weight acting on that box using this slanty coordinate system. Nifty. So that's step 2 for box 1. And before I move on to box 2, let's go ahead and finish out the equations for box 1. Let's do step 3 for box 1 before I move on to box 2. So for this, I want to generate some equations using F equals ma. I've already got my forces broken down. So the sum of the forces in the X direction is going to be this plus this plus this. So the tension in the string minus M1G sine of 30. And that's going to equal ma, but we're talking about box 1, so the m in question is the mass of box 1. It's going to be times the acceleration of box 1 in the X direction, which we don't know yet. We'll figure it out. So that's one equation. The second equation is going to be in the Y direction. The sum of the forces in the Y direction is going to be all the J's, this plus this plus this. So N minus M1G cosine of 30 equals M, and again, we're talking about box 1, so the M in question is mass 1 times the acceleration of box 1 in the Y direction. And of course, when I get to this point in the problem, I like to pause for a second and ask, do I know anything at all about the acceleration of that box? And I do know one thing right off the bat. That's that this box, if it slides, it might slide up the ramp if this guy's heavy enough, or it might slide down the ramp if this guy's not heavy enough. But what it won't do is it won't be moving in the y direction. It's going to slide along the ramp, which is the x direction, no matter what. So no matter what, this acceleration in the y direction has to be 0. This could go either way. I don't know what that is, so we'll have to solve for that. So there are my two equations for box 1 right off the bat. Whew, super easy. Now, let's go back and do the same steps for box 2. Now, for box 1, I picked this slanty coordinate system. For box 2, it's moving up and down, right? There's no reason to pick a slanty coordinate system for box 2. So I'll pick a more normal coordinate system for that. However, there is one caveat that I want to point out. One thing that's super easy to screw up. In fact, a few years back, we had another professor here at JCSU who's teaching physics, and he was doing a problem like this, and he would set it up. He couldn't figure out why he was getting it wrong. He was making the mistake I'm about to describe. So even other people who are like at graduate school level can sometimes screw this up. So the trick is this. When I choose my coordinate system for box 2, I want to make sure that it's consistent. Because here's what's going to happen. I know that if box 2 falls downward, that means that box 1 is going to travel upward. Meanwhile, if box 1 traveled downward, box 2 would be traveling upward. So they're going to move together. They're connected objects. So whatever acceleration this guy has up and down, this guy's going to have the same acceleration along the ramp. His x acceleration and his y acceleration are going to have to be the same number. But because of that, I want to make sure they have the same sign. I wouldn't want to choose a coordinate system where this guy had an acceleration of -5, but this guy had an acceleration of +5. I'd want them to both be positive or both be negative at the same time. So since I called up the ramp the positive direction for him, and if it moves up the ramp, he's moving down, I'm going to go ahead and choose down to be the positive y direction and x to be the positive x direction to the right. So what's going to happen is gravity is pulling it downward. If this is going down, that's going up. So that way, when I solve for their respective accelerations, they're going to both be positive or negative at the same time. I'm consistent in that choice. And it's a super subtle thing that if you don't do it, it's going to look right, but you'll get the wrong answer at the end. So far, so good? Now, once I've chosen that coordinate system, now I can break things up. Notice both of these forces are in the y direction, but nothing in the x direction. So in the x direction, I have 0 equals 0. I'm not even going to bother writing that. But in the y direction, I could break it down like this, but it's going to be kind of silly. I'm just going to do it this way. It'll be the down forces minus the up forces. So m2g minus t. And that's going to equal, since we're talking about mass 2, that'll be mass 2 times the acceleration of box 2 in the y direction. So that's the one equation I get for box 2. I don't get one in the x direction because there's nothing happening in the x direction. However, from common sense, I know that whatever acceleration box 1 has going in the x direction, it's got to be the same as the acceleration box 2 has going in the y direction. So this acceleration and this acceleration have to be the same. So I'll be able to just drop the subscripts and just call them both A, right? And solve for A. If they could have been different, I would have had to leave them separate and solve for them separately. So now I've got a total of 1, 2, 3 equations and 3 unknowns. So what I want to figure out is what acceleration are we going to have? But the problem is I don't know how big the tension is. I don't know how hard those strings are pulling. So in order to solve this problem, I need to get rid of the tension. Well, let's take this equation right here. If I solve that for t, it would be super easy. All I got to do is add this to both sides. So I can say that T is equal to M1A plus M1G times the sine of 30. I just added this to both sides, so it shows up on the other side. Now they're both positive. So the tension is equal to this. Now, if the tension equals this, I can take this expression for the tension, go back to this other equation I haven't used yet, and replace the tension with this. So notice when I do that, I'm going to have M2G minus T, so it's minus all this, so minus M1A minus M1G sine 30 equals, and on the other side I have M2 times A. Now I want to solve for the acceleration. The acceleration appears once over here, once over here. I need to combine like terms. So let's get all the stuff with A's on one side of the equation, all the stuff without A's on the other side of the equation. So I'm going to take this and add it to both sides. I like to add this because it's negative. That way I get fewer negatives. So on the left-hand side, I'm going to have left over this. So M2G minus this M1G sine 30. And I'm going to have M1A plus M2A. That's M1 plus M2A. Piece of cake. So now let's solve for A. I have M2G minus M1G sine of 30 all over M1 plus M2. There's my acceleration. Now, what acceleration is that going to be? Let's plug in the numbers. What did we say M1 was? We said M1 was 10, M2 was 12. So let's crunch some numbers. So I'm going to have 12 times 9.8. That's 117.6 minus 10 times 9.8 times the sine of 30. So this entire numerator is positive 68.6. This number was bigger than that number, which means my boxes are going to accelerate in the positive x direction. So 68.6 divided by 10 plus 12, so divided by 22. I get an acceleration of 3.12 meters per second squared. So what does that tell me? Well, since I got a positive answer for A, that means that my two objects are going to move in the positive direction. So what I said the positive direction was? Up the ramp. So apparently what happened was box 2 was sufficiently heavy that it's going to fall downward, pulling box 1 up the hill, right? Had I had box 1 be heavier, then what would have possibly happened is this might have been a negative, or this thing up top might have been a negative number. So if box 2 was super heavy, it might have slid down the ramp and dragged that up. How would I have known? I would have gotten a negative value for the acceleration, and I would have been like, oh, what does negative mean? Well, I said positive is this way, so negative is the other way. So by solving and seeing the sign of my answer, I can tell which one goes which direction. Now, once I know what the acceleration is, if I wanted to find how much tension was in the string, I've already solved for it. T equals all this garbage. So I can just take M1 times this plus that. So 3.12 times what was M1 at 10 plus 10 times 9.8 times the sine of 30. So I get about 80.2 newtons. So this was a connected object problem compounded with an inclined plane. And again, we just rolled out all the tricks that we learned, right? When we have inclined planes, we pick slanty coordinate systems and we break them down accordingly. For connected object problems, the trick is to do the free body diagrams for both objects and get equations for both objects, and to know that if they're connected, they're going to have to accelerate in the same way in at least one dimension. Here, the x direction for this had to have the same acceleration as the y direction for this. And that allowed us to use the accelerations and have them be the same. And at that point, it turns into a math problem. Super easy. How are we feeling? All right, so in terms of like how complicated I can make stuff, that's pushing my limit right there. Now, in terms of like where we're at in terms of your homework, we've pretty much hit all the stuff in chapter 4 at this point. Chapter 4 has introduced all of Newton's laws. We've learned how to solve some of your more basic problems. And what's going to happen in chapter 5, which is called Applications of Newton's Laws, is we're just going to learn some specific tricks that you can apply for specific kinds of forces that have their own little rules. And that's going to be the way we'll proceed. Specifically, the first thing that's going to get taught in chapter 5 is we're going to learn about how to deal with friction. So let's spend the rest of the time today introducing the concept of friction and figuring out how to solve a problem that involves friction. So in order to do this, we need to start with a general understanding of how friction operates and what friction does. So let's start something simple. Right? Here's a box. It's sitting on the ground. Right? Now, if that box is just sitting there and no one's trying to move it, there won't be a force of friction. Friction is a force that opposes motion. Or I should say that it opposes sliding. Motion. So what that means is if this thing is just sitting there, there's no friction required. However, if I walk up and I push it with a force to the right, then what would happen is this box would try to slide against the ground. And the friction is a force of contact between it and the ground. And it wants to oppose that sliding force. So this thing is trying to slide to the right. The friction would be in the opposite direction. It would try to slow it down. And as a consequence, it would slide more slowly than it would if there were no friction. However, if I take that same box and I reverse course and I push that box to the left, friction doesn't want it to slide left either. So the force of friction would be the opposite direction. Right? If I've got an object sitting on a ramp, then what's going to happen is if there were no friction, this thing would just slide down the slippery ramp, right? Friction wants to oppose that sliding. So just sitting a box on an incline, the friction is going to be up the ramp because what's happening is gravity's trying to slide it down. Friction doesn't want to let it. If, however, I was in the process of pushing the box up the ramp, well, friction doesn't want to slide up the ramp either, so it would always oppose. So when it comes to the direction of friction, if you want to know the direction of the frictional force, here's what you know. One, it's always parallel to the surface. And two, it opposes motion or anticipate motion. In other words, if you have an object that's actively sliding, or if it's just trying to slide, friction is going to always oppose that. So if you ever need to figure out what direction the force of friction is, you should always ask yourself, what would happen to this object if there weren't any friction? Figure out what direction it would be moving in that case, because the friction is going to be the other direction. If it would naturally want to slide down the hill, friction is going to be up the hill. If the thing is trying to slide, is sliding up the hill, friction is going to be down the hill. So ask yourself, what would happen without friction? Friction will always oppose whatever that is. In a lot of ways, the friction is just one component of the force of contact with whatever object you've got. Because think about it. If this box is sitting on the floor, there's going to be two forces, right? There's the normal force from the floor. The normal force is like perpendicular to the surface. The friction is like parallel to the surface, which means the normal force and the friction will always be perpendicular to each other, always. And you can kind of think of these as like the two different X and Y components of the force from the floor. Together, the force of the floor is the combination of those two things. So we know that. Here's something else we know about friction, right? Not everything creates the same amount of friction. Friction depends on the material. So if I have two different surfaces sliding against each other, the friction can be different from another pair of surfaces sliding against each other. If you've ever gone bowling, right? My grandparents owned a bowling center, so I spent a lot of time at the bowling alley. You ever go bowling, they make you put on special shoes. Why do they make you put on special shoes? Well, because when you throw that ball, that last step as you deliver it is supposed to be a slide. So you need shoes that are going to slide nicely on the surface of the approach. Now, if you try to do that in your regular street shoes, you're going to have way too much friction. You're going to put your foot down, it's going to plant, and all your forward momentum is going to be like, ah! You're going to fall over and look stupid. Your friends will laugh at you. It'll be hilarious. One of the things that I've often had happen when I was at the bowling alley with my grandparents is if you take those bowling shoes and you step in something wet, what happens is it changes how much friction you get from those shoes. They stop being slippery when you get them wet. And so somebody spills their soda, you step in it, you go to throw the ball, and your foot plants and you look stupid. But that's what it is. Different materials have different amounts of friction. So our model for friction is going to have to reflect that fact of life, that different materials are going to have different amounts of friction. So wood sliding against wood will have a different amount of friction from wood sliding against asphalt. Here's something that is perhaps non-intuitive, but is true about friction. And it has to do with the fact that the friction does not depend on surface area. Now, turns out that this is a controversial statement. I was teaching class one year at CPCC, and I told them that the friction didn't depend on surface area, and I had a student flat out call me a liar. He's like, no, that can't be right. And it makes sense that you might expect that it should depend on the surface area. Here's a big old box of Expo markers, right? I take this box of Expo markers and I drag it across the table. There's a certain amount of friction, right? Because this entire surface is dragging against the paper. Now, if I take the same box of markers and I put it on its end and I drag it across the paper like so, you might think, well, gosh, I should have less friction because there's less of the box touching the surface. But it turns out that's not true. Turns out I get the same friction going this way as I do going this way. And the reason for that, the way to understand why that is, I got to imagine what's happening as I drag that object across the table at a microscopic level. Because even though this box, it seems like it's fairly smooth, if I were to zoom in on a microscopic level, what I would find is that that box is covered with tons and tons and tons of little microscopic hills and valleys. So it's, really microscopically complicated and jagged. And even this surface here, which looks shiny and super smooth, if I zoomed in on it, it would have its own microscopic hills and valleys. And so what's going to happen is you think that this entire surface is touching this entire surface. But in fact, when you put this thing on the table, it's actually only touching in a few select points. There's a little spot right here where they're touching, maybe a spot right here where it's touching, but there's also spots where they're not touching at all. You can't see it, but microscopically, there's only tiny little areas of contact. And what's going to happen is when I set this thing on the table this way, gravity's pulling this thing down, the table is pushing it up. And so as a consequence, I've got a free body diagram of N upward, gravity downward. And since it's not moving up or down, the normal force from it is equal to the force of gravity. So the table is pushing up on the box with a force equal to the weight of the box. And that's true whether I hold it like this or whether I hold it like this. The force that the table has to put on them is the same both places. However, when I put it on the table this way, that force of gravity is spread all over the entire surface. So the amount of that force that has to be borne by a particular square inch of that surface is relatively small. When I tip it on the end, what's going to happen is each square inch is going to have to bear a larger fraction of the total because there's less square inches this way than there are this way. Now, why does that matter? When I put it on the end, because each square inch has to bear more of the burden, the result is that these two surfaces, they get squished together a little bit more. And because they get squished together a little bit more, what's going to happen is some of these places that aren't quite touching now, when I squish them together more, these guys here, maybe they're going to get squished together and they're going to touch. Maybe right here, these two guys that are not quite touching, they're going to get squished together and they're going to start touching. So when I put it this way, even though there's less total area, more of that area ends up touching and I get more friction from that. Because the amount of friction will depend on how many places it's touching. When I put it on the flat side, they're not squished together as much. Some of these areas here can separate and the effective contact area is changed. And it turns out that those two effects basically cancel each other out. So that at the end of the day, it won't matter whether I'm putting it this way. Here, I have more total surface area, but fewer points of contact on that surface area. When I put it this way, I have less total surface area, but more of those places are touching, and the two things basically cancel out such that the amount of friction doesn't depend on the surface area. And one semester at CPCC, I told the student that, and he's like, no, that's not true. And the reason that he just did not believe that that was true was because he was a NASCAR fan, right? He watched a lot of NASCAR races, and he knows that you got to have friction between your tires and the road to grip the road and make it around a turn. So he knew that the tires in NASCAR, they wanted lots of friction for better handling. And he also knew that the tires on a race car are different from the kinds of tires that you put on a regular car. Because on a regular car, you've got tread. Here's the side of the tire, here's the bottom of the tire, and you've got these little grooves, right? Here's the road down here. So you've got those little grooves on a regular tire. But on a race car tire, no grooves. And in fact, the tires are often very, very wide. They're wide and no grooves. And he's like, no, 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 you've got to be wrong, Professor, because I know they do this for race car tires because they want to have lots of friction. So by having more of the tire touch the road, that will be more friction. That's what he was convinced of. Turns out it's wrong. That's not why they do this. You get the same friction from this tire as you would from this tire. Same friction. So what is the advantage then of doing your tires like this? Because they wouldn't do it on race cars if there wasn't something about it that was good. And the answer has to do with wear and tear. If I go to my favorite little site, and I look up the friction sim, you imagine that this is like a microscopic sort of view of two objects rubbing. Here it's like a chemistry book and a physics book, right? Now what's going to happen is, even though those books both look flat, their surfaces, if you're looking at atom by atom, there's probably little jagged hills and valleys. And so when I rub those things together, I'm getting friction. Now, what's going to happen is, notice as I drag them together, watch the thermometer, right? I drag them together and it's causing my little molecules to vibrate around a little faster. That means their temperature goes up. That's why, like when you rub your hands together, your hands get warm. That's what's happening. Now, if I do a lot of continuous rubbing, like I am during a race when the tires are constantly rubbing against the road, what's going to happen is eventually I'll get some of these things so hot that the bonds that hold them together start to fray. You notice how the shape kind of changed a little bit? It's like I'm causing little microscopic melting, and eventually if I do it hard enough, I'm going to rub away some of my surface. So what's happening during that race is you're constantly wearing your tires down, right? You generate enough friction that over time you've drastically worn down the surface of your other tire, and that's why your tires have to periodically get replaced. Now, if you're a race car driver and you're running a race that is going to last like 500 miles or something, every time you have to stop to replace your tires, that's time that you're not racing, right? Every pit stop's slowing you down. So they want to do as few pit stops as possible. So by having a whole lot of surface area and no tread, it means you can wear them down a lot more before you have to replace them. You don't have to swap them out as much. If you had this tire, what's going to happen is these things are going to get worn away way, way more quickly. They'll have to replace those tires more frequently. So that's why they do it. It's not for amount of friction. It's to make the wear and tear even and more predictable so that they don't have to do as many pit stops. Now, I'm a cheap person, and I hate having to buy new tires for my car. And if doing my tires like this would make them last longer, why the heck wouldn't I do my regular Prius tires like this? Why do I have tread if I'm going to have to replace these more often and buy more tires? Well, the answer for that has to do with water, right? If you're a NASCAR racer and that race is going on and it starts to even drizzle, even the tiniest bit of rain, they shut that race down. They cannot race in the rain for anything. And the reason is because if you drive this tire over a puddle, so here's a little puddle, what's going to happen is as the tire rolls over that puddle, the water is going to have to splash out from underneath the tire around the side. Now, the faster you're going, the less time the water has to get out of the way. And if you're driving too fast, the water can't get out of the way. And when that happens, your tire's not touching the road anymore. Your tire is touching a thin layer of water, and the friction from water is way less than the friction from the road. And at that point, you're what they call hydroplaning, right? And when you hydroplane, you get very little friction, and suddenly you lose control of the car and you crash and die, right? So hydroplaning is a death sentence for these guys, because if they drive even a little bit fast, and they're driving a lot fast, the water can't get out of the way quick enough and they lose control. Now, what happens when I drive my tire over the puddle? Well, what's going to happen is, for my tire, I've got these little grooves. And yeah, some of the water can splash out over the side, but some of the water can channel up into these grooves. Now, the water that does that doesn't have to travel quite as far, which means it doesn't take as much time for it to get out of the way. That means that I can drive across that puddle a lot faster before I start to hydroplane. So by having tread on my tires, I'm able to drive in wet conditions more safely than I otherwise would. And in fact, as your tires start to get bald, it's not that you're getting less friction, but man, the minute it starts to rain even a little bit, you're going to be spinning your tires and skidding and all kinds of stuff. That's where you know you're in trouble. So wet weather performance is way, way less on a bald tire than it is on a tire treaded. And that's what that's all about. It's not about how much friction, it's about how you maintain friction in different conditions. If I only ever had to drive when there was no rain, this would be the hands down better way of doing it. So friction doesn't depend on contact area. It does, however, depend on how hard those two surfaces push together. So as a corollary, it depends on the normal force. The harder I squish those surfaces together, the more of these little areas squish into place and the more friction you're going to get. That's also has an implication for race cars. Because think about it, a lot of race cars, you got this like spoiler in the back. Now, aside from looking really awesome, what's the point of that spoiler? Well, when you drive your car, the air has to flow up over and around your car. And of course, if your car pushes the air up, that means the air is pushing your car down. Newton's third law. Now, what's going to happen is when you have that spoiler, you get a little extra push up. You're pushing more air upward, which means you get more downforce from the air. Why would I want downforce? Well, because I want traction, I want friction, and the friction depends on the normal force. So by pushing the air up, it's pushing my car extra down. I'm going to get more normal force than I usually would. And by having that extra normal force, I get extra friction. So they're going to get better traction at high speeds from having a spoiler than not having a spoiler. That's what it's all about. So to put all of this together, we're going to build a model. And that model is going to be the following. Oh, wait, we got one more. I almost forgot. One more observation about friction. Let's do a number 6. And it turns out that the amount of friction you get is going to depend on whether you're already sliding. There's less friction between surfaces that are sliding. So if I have two surfaces that are actively sliding, then what's going to happen is this surface up here is kind of gliding across the bottom surface. So these little nooks and crannies, they're kind of skipping across and striking the bottom surface, but they're not really getting very well entrained. So if you're actively sliding, you just barely get settled before you skip off and hit the next guy. But what if these two surfaces are not actively sliding? What if they're stationary? Well, what's going to happen is when they're nice and stationary, all these little points of contact, they get all nice and snug and settled in. And when they get nice and snug and settled in, and you try to shear them apart, it's harder. You got to really work at it to get them out of their little nice snug hidey holes so that they start skipping again. So it takes more frictional force to break them free than it would if you were just opposing the friction as they actively slide. And if you've ever like pushed a big heavy object across the floor, you might have felt this effect. You might have found that like once you get it moving, it seems like it's easier to keep it moving. And that's not an illusion, it's true. But when it's stationary, you got to push a little extra hard to get it to budge. And once it starts to budge, it slides more easily. And that's an effect of that. So that's the last little observation about friction. And we're going to take all of these things and meld them into a model that we can use for friction to solve friction problems. So here's the model for the force of friction. We're going to say that the force of friction is equal to something called the coefficient of friction. The coefficient of friction looks kind of like a little scripty U thing. It's kind of a U with a little tail. That's actually the Greek letter mu. And this is called the coefficient of friction. So the force of friction is going to equal the coefficient of friction for whatever the materials are that you're rubbing against each other. If something is super slippery, then the coefficient of friction will be a small number. And if something is like super, super rough and highly frictional, like sandpaper, the coefficient of friction will be a large number. But usually it's a number between 0 and 1. But it'll be that coefficient times the normal force. That's how we're going to model the force of friction. Now, to make things a bit more complicated, since we have two different kinds of friction, we have the friction when you're sliding versus the friction when you're not sliding. This coefficient of friction is going to have two flavors, right? There's going to be mu sub s and mu sub k. Mu sub s is called the coefficient of static friction. Whereas mu sub k is the coefficient of kinetic friction. Now, static means not moving, kinetic means moving. So static friction is what you get between two surfaces that are not actively sliding. They're nice and happy and nestled in place. Kinetic friction is the friction you get when the two surfaces are already sliding against each other and the surfaces don't really have time to get nice and settled in. So in general, for most materials, the coefficient of static friction will be larger than the coefficient of kinetic friction. And if you look in your textbook in chapter 5, there's a little chart where they list the coefficients of friction for different kinds of materials. So for instance, I know that like for wood sliding against wood, the coefficient of static friction is about 0.5. But the coefficient of kinetic friction is lower. It's about 0.3. Right? For asphalt and rubber, the coefficient of static friction, I believe, is 0.8. And the coefficient of kinetic friction is something, I don't know, look it up. But it's less than 0.8. But in general, the static friction coefficient will be larger than the kinetic coefficient because things get settled in and they're harder to budge. So that's going to be how we find the force of friction. Now, a caveat. This is not the force of friction. This is the biggest the force of friction could ever be. The force of friction could always be less than that. So for instance, if I had a little box and that box has a mass of 10 kilograms and that box is just sitting there on the table, there's a normal force, there's gravity. If nobody's trying to slide that box sideways, there's not going to be any friction. The friction for this box would be 0. Now, how big would the normal force be? Well, the normal force would just be m times g in this case. That's 10 times 9.8. So the normal force is 98 newtons. Now, let's say this box is made out of wood and the floor is made out of wood. So mu s is equal to 0.5 and mu k is equal to 0.3. Now, if I walk up and I push this box to the right with 10 newtons of force, this is me pushing. Now, friction doesn't want this thing to slide. So if I push this thing with 10 newtons, the force of friction could be mu s times n. Well, mu s is 0.5, n is 98. So 0.5 times 98 is 49 newtons. 49 newtons is bigger than 10. So the frictional force would be the other direction. It would oppose the motion. But it's not going to be the full 49 newtons because that's crazy. That would say that I'm trying to push it to the right with 10 newtons. The friction is like, no, no, no. And it's pulling it way, way harder to the left. The box would be sliding left. But friction is not going to make it slide on its own. So in a situation like this, the friction would be less than 98 or less than 98 times 0.5. It'd be less than 49. It would just match and be 10 the other direction so that these things cancel. If I push a little bit harder, 20 newtons. Well, remember the friction could be as big as half of 98, which is 49. It could do 20. So it would just be, nope, increase to 20. If I increase to 30 newtons, that'll increase to 30. Now, let's say I increase all the way up to 50 newtons. So I'm pushing with 50 newtons to the right, but the maximum force of friction can only be 0.5 times 98. That's 49 newtons. The friction can't go up to match me. It can only go up to 49. Does that make sense? So this is the maximum force of friction. It could always be less than that. So oftentimes, if I want to be super, super careful, I will say that the force of friction is going to be less than or equal to mu times n. And it will be whatever size it has to be to try to prevent the object from moving. If, however, I pull 50 newtons here, if I'm pushing harder than friction can ever get, well, at that point, the net force will no longer be zero and this thing will start to slide. So once I push this hard, friction can't stop me anymore. This thing would start to budge. If I'm pushing with less force than this, it won't budge at all. And so that's how we'll deal with friction problems. So we'll do a couple of examples next time, but I think that's pretty much everything we wanted to get out of the way here. So have a good day. I'm going to try to post the kind of the mock-up assignment for your exam sometime today. That'll let you test some of the tech stuff for the exam. The exam will go live tomorrow. I'll try to get it as early as possible, but it'll be sometime tomorrow. It'll be due Friday at midnight. Make sure that you do the test mock-up assignment with your particular hardware, just to make sure that that it works properly before you start the exam. Because once you start the exam, it's open and you can't do anything about it. So I'd rather have technical difficulties on the test assignment than I would on the real exam. Any questions before I let you guys walk out the door?
Dr.
No,
Pruitt,
but
I have a
I'm gonna be in
question.
office hours.
Okay, I figured.
What is your office hours today?
So my office hours Monday through Thursday are 1 to 5.
Okay.
Between those times, just send me an email. I have my personal meeting room set up, and I'll make sure you get a Zoom link and you get in there and do that. But that's
Okay,
my
I have the link.
if like on Mondays, I tend to run a little late. So if you give me an appointment, I'll usually make time for you until about 8 o'clock Eastern. If you have other time, if those don't work for you and you still need a non-standard time, send me an email proposing a time and I'll let you know if it works for me. But those are my standard office hours.
Okay, thank you.
You're welcome, guys. Have a good one. Again, if you need an office hour visit, send me an email and I'll set it up for you.